Welcome back for our RI seminar series. It's my deep pleasure to introduce Ross Knepper for our RI seminar speaker. Before I go through what will be a great introduction, I just want to remind you all some logistics. We're going to have a seminar 3:30 to 4:30. Everyone wants to speak. And then afterwards, there is a post-seminar reception in the atrium for the sub-T team, our very successful sub-T team of which we're very proud. I'm saying this because we should be proud, not to make Cornell feel bad. But it's true. However, he takes pride because he's a Carnegie Mellon person. See, he got his undergraduate degree here at Carnegie Mellon in 1999. Okay, he actually, it doesn't say this in his bio, and I think these are the important parts of his bio that he skips. You can read the regular one online. But the important one is that he worked for me starting in 1996. He was my second undergraduate. I don't remember who the first one was, so that one probably didn't work out. Ross worked out very well. Then there's other stuff in his bio, and then in 2004, he worked for the Forestry Service in Death Valley.
National Park Service.
National Park Service in Death Valley. And then after that, one thing led to another, and here he is today. So, and then we wrote a paper together too, Snakes on a Plane. No, really, it was snakes on a flat plane. And it's Ross and Ross. So very excited to hear Ross. Please ask him lots of hard questions, because there was a time when he sat in the audience and asked the seminar speaker hard questions. So, without further ado, Ross.
Thanks, Howie, for the gracious introduction. And thanks to every one of you for being here. I really appreciate you showing up on such a beautiful day. So, I guess since we're revealing secrets from my undergraduate days in the last millennium, I have in computer science, but I also had a second major in history. And I'm actually going to start by talking to you about history today as an allegory for where I see the robotics field and where I think we're going. And I did this very, very conscientiously because, as Howie said, I was one of you all not that long ago. And I sort of have this feeling that I need to deliver some wisdom. So hopefully it's in there somewhere. All right, bear with me. So the story of 19th century America is the story of westward migration, manifest destiny. This was white American settlers moving west into lands that were occupied by not-so-white people. And according to this doctrine, right, we were destined to occupy the whole continent. So the frontier was moving westward, and the frontier lifestyle with it. What this lifestyle meant was the US government would give you 300 acres of land on which to build a homestead, conditioned only on the fact that you live on it. You plant your flag, you farm the land, you raise your family, etc. We kind of do the same thing in robotics, right, if you can allow me the metaphor. So here's my flag planting exercise. After I graduated with my PhD from CMU, I went off to the Massachusetts Institute of Technology and built IKEABot. So this is an autonomous distributed IKEA furniture assembly system. These robots are actually reasoning from basic principles. CAD files are given to the robots, and they think about their capabilities and the files and how the parts fit together. So they come up on their own, they come up with a blueprint. And then having a blueprint, they work together to come up with a sequence of actions which should assemble the robot. These actions are robot-specific, like using the gripper to pick up the leg or using the rotary tool to screw in the leg. Many of the others can be performed by either robot, right? So this was a pretty cool demo. I think there's a lot of interesting stuff in there. This paper is highly cited. Why? Because I was the first one to build IKEA furniture on a robot. Right? So that's flag planting. By the way, if you want a faculty job, this is actually not a bad idea because it's a brand. You know, you can build your brand. But at the same time, we're here to do science, right? Not build branding. So what does this mean for the state of the field? Well, let's go back to our little story. Westward migration eventually came to an end as the frontier reached the Pacific coast, right? So in 1890, the US Census Bureau actually officially declared the closing of the frontier. And what that meant was not that there was no more settlement, but that it had broken up. All of the best, most arable land had been farmed, had been settled, and what was left, no offense to anyone from Nevada, was a lot less desirable land, right? And so at this point, people are faced with a choice. Do we focus on the good stuff, or do we keep doing other things just because they haven't been done yet, right? And so that you can kind of see where I'm going with this now as a metaphor. So here are some lessons that I take away from this frontier thesis. By the way, for anyone who's interested, look up Turner's frontier thesis. So the closing of the frontier in robotics. I think that as industry discovers robotics, which it has, in a big way, there's a lot of engineering resources that are being brought to bear now on this field. That gives us, as researchers, an opportunity, and I think an obligation, to do things that are not what industry is doing and that complement what industry is doing. Perhaps that means that we should take a slightly more scientific mindset and leave the hard engineering problems to the people who have the most money to solve them. Perhaps that means we should work on fewer, larger problems so that we can all agree a little bit more on what are the key problems that we need to be solving. I think one thing that we don't do well enough in robotics is replicating the results that other people have produced. And I think that flag planting is a big piece of that. Everybody wants to do something new and not show that something else that's been done actually is legitimate and real. And I think we need to take a cue from other fields like computer vision that are really good about standardized benchmarks and metrics. But on the other hand, we in robotics need to be careful not to be too beholden to these. We've seen other fields where the field is basically steered by what happens to be the prevailing benchmarks. So those are my insights. You're welcome to criticize me at the end of the talk if you disagree. But what I take away is actually the opposite of something that Matt Mason taught me. So he's not in the room right now, so maybe it's unfair to pick on him in his absence. But he taught me that when you're looking at a problem, you want to take the simplest instance of that problem and figure out the bare essence of it, distill it down, and solve that problem, and then generalize. What I'm going to talk to you about in this talk is actually the reverse. So this is what's called the Eisenhower Principle. If a problem cannot be solved, enlarge it. So big problems, right? Problems that cannot be solved at small scale. A lot of these happen in the context of social robotics. So when you introduce people into robots, things get complicated. Let me give you a few examples to inspire where industry comes into play. So the first one, and by the way, I presented this with Anka Dragan in the room, another CMU alum who's at Waymo and is in charge of fixing this problem. Here's a Waymo car trying and failing to merge in heavy traffic. And you'll notice it turns on its blinker and just politely waits for a gap to open up. This is not really how human drivers operate, right? If nobody's going to let you in, you have to start to nudge or nose into a gap maybe to get it to open up. But this vehicle is what we might say it's a little too timid, right? But really the problem is a social problem, which is it doesn't understand the social dynamics of people. We are a team on the road, and we're all trying to get where we're going without any crashes. And if you understand the way that those team dynamics work, they will work for you. Completely different problem. So DeepMind a few years ago solved the game Go, which is the super hard game. And they've decided now the next big game that they want to solve is a card game called Hanavi. I'm going to tell you a little bit more about this game because this is something that I find very interesting in my own work on teamwork. So in this game, you hold your hand backwards, so you can't see what cards you're holding. Your partner's cards are visible for you. And by the way, this is a collaborative game. The goal is to play cards down on the table in the correct order to build up each color from 1 up to 5. And you have to do this, of course, without being able to see what card's in your hand. There are 3 possible hints that allow you to achieve this task. The first one is you can play a card and then draw a replacement. The second is you can discard a card and draw a replacement. And then the third one, which is what really enables this, is you can give a hint. So hints work like this. You can talk about a color. For example, you can say 3 blue cards. You must give all cards of that color. Or you can hint about number.
So you have 2 blue cards. It must be all cards in the queue. Those are the only communications allowed in this game. So it's pretty limited. And you'd think that people would, for example, give a hint about a color and then a number, and then you know what you're supposed to do. But that's actually not how this game tends to play out in practice. So what it looks like in practice is something more like this. So this is my student, Claire, on the right. She gives a hint to her friend, this is a blue card. And her friend is going to play the card. So she knows it's blue. She doesn't know the color. But she trusts that she wouldn't have received that hint unless it was a playable card, right? So it was actionable information that was relevant to the task at hand. That's teamwork, right? So let's talk about teamwork a little bit more broadly. Teamwork is really the confluence of 3 things as a system. There's communication, which is natural and multimodal and messy. There's coordination. These are basically consensus and synchronization problems. And then there's representation, right? What is the set of symbols that we're trying to coordinate over using communication to solve a task? So the system occurs when you start mixing elements of 2 or more of these together. And these are problems that cannot be solved without considering them simultaneously.
For example, team decision-making is a combination of coordination and communication. I'm going to talk about implicit communication of actionable information, which is communication growing down towards the other 2. And then at the end, I'm going to spend about half the talk talking about multi-agent social navigation, which is it's really the whole thing, but I had to make it look pretty impressive. So let's dive in by talking about some real robot problems. So just to give you a sense of some of the sort of context in which I want to think about these team dynamics, this is that IKEA-bot system that I showed you before. We did a user study in which we wanted the robot to be able to ask for help. So when a failure occurs, we want the robot to be able to get a user's attention and then say something that is understandable as natural language so that any untrained user can understand what to do. So in this case, the robot says, please give the blue robot the white leg that is on the back table. And you notice he doesn't immediately drop what he's doing. He actually finishes, gets to a good stopping point, because he's already internalized what he needs to do, because it was a clear help request. The help request was actually generated contextually by leveraging the information around. There's more than one white leg, so saying, please hand me the white leg might have been ambiguous. Therefore, the robot wanted to add a little extra. But you notice that the robot was basically directing when it needed help and when it didn't. And so that it could...
Question?
Yeah.
When a human being is doing a task, there is some cognitive overload. If you give them too many details, put this on this on.
That's absolutely true. Yes. Yeah. How much to convey? That's a hard question because it depends on the individual. It also depends a lot on the context. The way that people solve this is by taking a guess, and then if communication breaks down, we do a repair. I'm going to talk later on more about repair, but this is actually a core part of dialogue. We think of dialogue as being, I say a thing, you say a thing, et cetera, but a lot of it is actually just trying to understand the things that we already said. And so that's something that robots don't yet know how to do, and that's something that I'm working towards. Thanks for the question. Yeah, so this sort of a collaborative furniture assembly context would be one place that we're interested in this sort of capability. Another very different one involves navigation. So I mentioned we're going to talk some about social navigation. So here the robot is navigating just as the CS colloquium at Cornell is letting out. There's a lot of traffic around, and you notice it just cuts off somebody, right? Very rude. It doesn't understand social rules, and so it can't anticipate that somebody intends to move in a certain way. So that's something we'd like to avoid. Here's another example real quick just to show what can happen. In that case, he was looking away, so he didn't even realize the robot was coming towards him. But a human would see, oh, that guy's looking away, so I need to avoid him. He's not going to avoid me. So these are things that robots can do if we give them enough, if we equip them with the information to solve these kind of problems. Okay. So first off, there's a huge amount of work that's already been done in teaming, in social interaction, in psychology and AI in a lot of different areas. This is only a small subsampling of the work that I'm leveraging in what I'm going to talk about today. Next point I want to make is if you have n agents in a team, there's actually n+1 decision makers because the team itself is trying to make decisions. And that consensus problem is hard, but in the end, that's what matters, right? All of the members of the team come together to form a consensus and make progress. So we can actually look at this from a systems perspective as a distributed systems problem. We have joint actions that multiple agents are taking. We need to form consensus and synchronize our actions. We need to communicate over multiple modalities, and actually a lot of the communication is implicit. And finally, this implicit communication is defined as requiring context in order to interpret, right? So it's not enough just to listen to what people say. You have to be looking at what's happening while they're saying it in order to truly understand. All right. So what does this actually look like? The stuff I've just been saying, what does this look like in real people? I want to play a short video just to inspire you. So I told you about this card game Hanavi. And this is from an exploratory study that we did. We'll just let this play. These are novice players, by the way. So they know the rules, but they don't know the strategy. They're trying to figure out the strategy.
We're not allowed to say that. I'm pretty sure it's pretty bad considering.
Wait, I don't know what to do.
Right? There's like very little things.
Wait, you told me that this was...
There we go. Okay, sorry about that. People trying to negotiate a strategy. And technically, they were cheating like crazy in the card game of Hanavi. Because they're talking. They're actually leaking a lot of information. Right? And so the part you didn't get to see is, why did you tell me my hand is green? What does that mean? And they haven't even come to agreement about what does it mean when I tell you that one of your cards is green. Like, should I play it? Should I not play it? So in Hanabi, this is considered cheating. But in any other team context, I would just call that good teamwork, right? They're trying to come to agreement, as rational human beings do, about how they should proceed collaboratively. And this is exactly the stuff, as messy as it is, that we want to try to capture, right? So can robots do that? Well, this is a tough domain in which for robots to do that. So let's look at a different domain that's a little bit simpler, social navigation. And we want to figure out what aspect of this problem truly needs to be decided by the team, and what part of it can we actually leave to the individuals, just delegate to one person to solve all by themselves, right? Because if we can make that distinction clearly, then the problem becomes a lot easier. So here's a robot. It's trying to navigate among some people. The people are moving unpredictably. So maybe it tries to predict a trajectory that it wants to follow to avoid people, right? Why is this hard to do? First of all, there's an infinite number of possible trajectories that you could pick. Why should we favor one over another? There are lots of techniques that will tell you you should follow exactly this path, but there's no obvious reason one of them should be right. And secondly, people are reactive. So even if that were right in the abstract, as soon as the robot starts moving, people are going to respond to its motion in a socially competent way, because people are normally socially competent. And so that will invalidate what the robot had just planned to do, if the robot is not socially competent itself. So what do we do instead? Well, we need to divide this decision problem into two aspects. On the left, we have the individual decision-making problem. This is about maneuvering and social signaling. And this is captured by the geometric shape of that path, right? On the right, we have the team decision-making problem. This is inherently topological. Are we going to pass each other on the right or on the left? So this deals with collision avoidance and consensus. So two completely separate problems, one individual and one team. And if all of the agents can agree on this separation, then we can actually efficiently solve the team problem without even needing to worry about the particulars of the shape of the trajectory that each of us is going to follow. What I've just observed in navigation actually generalizes. So in general, in team contexts, there's an agency of decisions on a sliding scale from individual to team that matches with the granularity of action. So the more team-oriented an action is, the more coarse-grained it necessarily needs to be, because it's limited by our ability as a team to come to consensus about how we are going to act right now. All right. That said, I'm going to shift gears a little bit. I'm going to talk to you about implicit communication. So this is the entanglement of action and communication. Because unlike robots, which tend to think that those are two separate things, humans actually entwine them and treat them as both being communicative, right? If I do a functional action in a team, everybody in the team is going to observe me do that and read into why did I choose to do the thing the way that I did. So robots are missing half the conversation if they don't tune in to the implicit part of that conversation. So just to set the scene, say we have a human and a robot. They both have some private knowledge, right? And the private knowledge may overlap some of it, but they don't both know that they both know that private knowledge. There's also shared context. So that comprises some public knowledge. In particular, a set of actions. So if I need to perform a certain functional action, like screwing in a table leg or, sewing a blanket or whatever it happens to be, there are many ways of doing that. So AF is the set of all possible functional actions that I might take to accomplish a certain task. And then there's a distribution that describes the likelihood of seeing any given action in a particular context. That is, when a certain set of facts are true, how likely is it to observe that action? And cognitive science tells us that people actually have some version of that distribution in our brains, right? Okay. Now, the way that this is going to unfold, in this case, the human has a fact, which he'd like to convey. He wants to do it implicitly. There are many good reasons for that, which you can ask me later why, if you want. Rather than doing it explicitly, he's going to encode this fact, M hat, as an action, and he's going to perform that action. So maybe he's doing a functional action at the same time as he's also communicating this fact, right? Okay, now the robot is going to observe that action that the human performed and then decode it back into the same fact. And under the right set of conditions, now they both know that they both know it, we can treat that as being part of the common ground. Okay. So those two green bubbles are basically what I'm going to describe to you right now. How do we do that? This is based on insights from psychology that people connect action and goal. When we observe one, we think about the other one automatically. This is just something that we are hardwired to do. Some work that was done here, actually, in 2014 by Anka Dragan and Sid Srinivasa divided these two directions and gave them both very handy names, which I'm going to revert to now. If you know the goal that somebody has and you're able to guess the action they perform, we would call that a predictable action. If, on the other hand, you know the action because you observed it and you're able to guess the goal that that person had in mind when they performed the action, we would call that a legible action, right? So not all actions are one or the other, but many are. So how can we think about these? There's a set of actions which we parameterize as a continuum. In this case, we have our probability distribution, and we note that some actions are much more likely than others, right? So most often we expect to see the probable or the predictable actions performed. But on some occasions, you will observe a surprise. Somebody will perform an improbable action, and when you see that, you don't just say, huh, that's weird. Right? You don't treat it as a fluke. You actually ask yourself, now, why would somebody do that surprising thing? That's why we call that a legible action. Now, the key to decoding this at this level is we're searching for a fact, if we're the observer, we're searching for a fact that would explain this improbable choice. And you know that you found the fact, the M hat, because it changes the shape of this distribution, if you assume it, such that that improbable action now appears to be probable to you. A nice consequence of this is that if you already knew M hat, then that action that the person chose to do was just predictable in the first place, and it doesn't even trigger any inference. Yeah?
No, I would say, why don't you think that the person changed
That's possible.
That's the point. This is basically the Atlas latest work on adaptive intent inference, right?
Yeah.
And so that's the most probable thing.
Well, I mean, most probable depends a lot on the context, right? So if you see a surprise, it's possible that the M hat that you're searching for is the person changed their goal, right? That's one possible explanation. Another one is they have the same goal, but there's some other fact that you don't know that is a surprise.
So I was also curious.
Mhm.
So her question, I like this. It made me think about when there's a discrete change. I
Yeah.
understand because continuous changes you can track things, but if there is a discrete change, do you have some like measure, some innovation that says everything's completely wrong and you start?
Right. So I guess there's a few caveats. This is a deliberately very abstract model of implicit communication because I want it to apply to all domains, right? So I don't tell you how to compute this probability distribution in particular. So I think all of the details that both of you were asking about just now are really encoded in the shape of this distribution. And that's something that in practice we end up just learning. You know, when you believe a certain set of facts to be true and you observe a surprising thing, it probably means, oh, you know, Katya, you changed your goal, right? In other contexts, it might mean something else. So that's basically, I mean, all the skeleton in the closet, if you will, is buried inside of that. And these are hard problems, you know. Which of the seemingly infinite number of facts that are contained in the common ground, the sky is blue, right? Is that relevant to the inference problem? Probably not. And I'm not telling you, how do you know which several facts are relevant in the current moment, right? That's a separate problem that I'm not addressing here. But I think it's another critical piece of this puzzle. Yeah. I will show you. I'll show you, well, at a small scale, yeah. This is partly this is meant just to be descriptive of a phenomenon. Because the details are, I mean, people are complex, right? This is describing all that ugly Hanavi stuff that I showed you earlier. There's a lot of details that this is sweeping under the rug, you know.
But I think you started with the idea.
Yeah.
There, I think you can create this formula.
Yes.
You look at all the instructions,
Mhm.
sets of idea, and you measure all the instructions.
That's right.
And that could be the actions.
Yep.
So that's a very well prescribed domain.
That's right.
So is that the first thing to try?
So the first thing to try, in my opinion,
The game thing is much more complicated about intent and so on.
yeah. So in my opinion, the first thing to try would be to divide between task and team. So there's a certain number of things which you were just describing for IKEA that are very task specific. You know, do I need a screwdriver right now? But there's some that are actually team specific, like did the goal change? That's actually completely independent of the particular task that we're doing. And probably there's a common set of social signals that are going to tell you, hey, my task changed. You know, it might be something in the facial expression or the tone of my voice that's telling you this. And so I think being able to label or classify a particular set of, you know, multimodal inputs, the action, as being, this is more likely to describe a task or a team piece of information, I think that's the first step. To my knowledge, nobody's done that yet. All right. So here's the math for how to decode an implicit communication. Basically, we're searching over the set of all possible explanations for the one that's most likely, given the action that you saw in context. And note that that's the wrong form for what we said the brain has in it. So we actually need to flip this around using Bayes' rule. And when you do that, you get this extra term on the end, the prior. And the prior is actually really important because if you're trying to explain a surprising phenomenon that you saw, you want to pick the most likely explanation that does it. In other words, you want to avoid conspiracy theories. So that's what this does. What about the generation side? On the generation side, we need to pick an action out of the set of functional actions that would accomplish the task that we're trying to do. And we want to pick the action that's going to make that fact most likely in context. Right? Again, we need to flip this around using Bayes' rule. And here we see it's going to give us the ratio of the action knowing the fact over the action not knowing that fact. In other words, we want to maximize that rise because that corresponds to the signal strength of the implicit signal that we're sending. Right? There may be other considerations. For example, some actions may be more desirable than other actions. And I'm going to claim that that's actually encoded in P here. Yeah?
Why do you want to optimize to satisfy? Why do you want to find the best action, which could have high cognitive load?
Yep, that's fair.
Versus one that is good enough to move it into the predictable.
All right. So it's confession time. You actually caught me. I think probably this is satisficing. The existence of a big rise is actually irrelevant as long as you found an action with a big enough rise somewhere that would explain the particular fact, right? And I agree with you that finding the absolute most, the highest rise is actually not tractable. And there's other factors that come into play, like it may be much more costly to us to perform the action that has that bigger rise too.
So that was going to be the next question, which is why are you not taking cost into account?
Yeah. So as I said, this is a deliberately simplifying model just to analyze the communication side of things. There's a separate question of how do you trade off cost at a functional level with the communicative cost of ambiguity, right? Because you could always pick a different action that might lead to a smaller rise and hope that it's clear enough. And we actually do this all the time.
We do it all the time. So why do you think you can separate that, not consider cost in the model, whereas in my mind it's critical?
Right. So cost is in the model, but again, it's buried in P. Because you're not going to pick an action that's very costly if there's a substitute action that would be better.
No, you're trying to maximize the probability.
Yeah.
You're not trying to minimize expected cost, minimize expected cost or something like that. I don't see that you can separate the cost. If you want to do something that is similar enough to the way humans behave, I don't think you can separate the cost from the probability.
I very much appreciate the point. I suggest we take it offline. I'd love to debate it further.
Another thing.
Yeah.
Have you looked at all at dialogue, coherent dialogues? This is exactly what the
Yes.
our LTI friends
Yes.
are doing, right?
Yes.
Because if I have an utterance in a context, and
Yes.
I need to calculate what my next utterance is going to be so that our conversation is coherent, this is exactly the kind of
Yes.
calculation, and I'm sure they have
That's right. So lots of people have done this before me. Right. So if I were the first person to discover this, I'd be a whole lot more famous than I am. What I did was realize that all these people are actually doing the same thing. Yeah, no, I hadn't gotten there yet. So you're too quick for me. All right. But I wanted to make one more point, which is the similarity of the generation and the understanding step is actually kind of striking, right? We're doing almost the exact same optimization, except for which variable we're optimizing over. And the reason for that is that we have the same goal. Whether we're generating or understanding, we want to maximize the confidence of the observer, of the understander, right? So if I, as a generator of an utterance, am trying to maximize my own confidence at asking for help, I'm not going to say, please give me the white leg on the black table. I'm going to say, please help me. Because that is undoubtedly right. Whereas maybe the black table is actually gray, right? Or something like that. And maybe I'm going to cause confusion. And there was a question earlier about adding more detail. This is exactly the same point. Sometimes it's a good trade-off to add more detail to your request when it serves a clarifying function for the listener. Whereas detail just for the sake of detail is going to confuse and not clarify. So that's where this comes out. All right. So we have to have real robot videos, right? So this is a robot actually running what I just talked about. So it's hot and a sort of a stop gesture. And he's actually doing simultaneous speech and gesture understanding. Similarly, So basically, if you hear things like it's hot or it's heavy, out of context, that's really confusing, right? It could mean the soup is hot. It could mean it's hot in this room. But in the context of the action that the robot is currently performing, there's only one reasonable interpretation for what the person was trying to convey. And so the result of that is that people are allowed to act more like real people, right? If you were trying to program the robot to avoid grasping the tip of the soldering iron, and you weren't allowed to exploit context, you'd have to say something like, Baxter, add a new grasp selection metric to exclude the chip. And then when the robot is about to burn itself, I don't know anybody who can just whip that off just like that. So I think it's natural that we do things like say, it's hot, or stop, because that's just what we know how to do in a split second. And so you need to be able to understand the implicit meaning behind these very ambiguous things.
These kinds of communication scenarios, the latency is really jarring.
Yes.
So how would you expect humans to even communicate naturally? So they're hot, and then
Yeah.
30 seconds.
Yeah, I mean, it's an amazing thing that we can encode and decode implicit messages in a split second. And I think the answer is we're actually learning it. It's that most of the interactions that we do all the time, it's not the first time that we've had this sort of a conversation. So you understand the implicit meanings.
What I'm asking is, where is the computational, or where is the latency coming from?
Oh, in the demo?
Yeah. Is it because you're using a slow computer?
It's a slow robot, slow computer.
Algorithm or
Yeah. I mean, he clears his arms out of the way so the computer vision can localize everything on the table. And like this is not an optimized demo for real-time performance. Yeah. But the inference is quick because we constrained the set of possible explanations to be small. If this were a wide open world, then the set of possible explanations becomes huge, and we don't know how to deal with that yet. Right? You could ask a question. Are you talking about the temperature of the tool that I'm supposed to pick up? Yeah. And many people have looked at that problem too. All right. So what's going on here? This is a type of inference. I'm going to talk about 3 types of inference. First off, deduction. If I know that A implies B and I know that A is true, then B is true, right? That's traditional logic. Secondly, induction. If I know that A is true and I know that B is true, then maybe A implies B. This is not hard and fast rule, but this is basically the pattern in machine learning and in Bayesian inference that we see all the time, right? But there's a third combination that we can look at here, which is called abduction, abductive inference. If I know that A implies B and I know B, then maybe A is true. Maybe A explains B, right? And so it's called inference to the best explanation. The first 2 were known to the ancient Greeks. The third one was first described by C.S. Peirce in 1901, which is kind of interesting. But abduction is something that we all do all the time, every day. It's a survival instinct. There's rustling in the bushes. Maybe it's a wild animal. So we wouldn't have evolved to get to this point if we didn't have this abduction capability. And I think it's something that we need to explore a lot more in robotics. It's something that was in vogue in the 80s in AI for doing things like medical diagnosis and crime solving, really hard explanation problems. What I'm talking about here is actually relatively much easier explanation problems. So I think this is something that if you're looking for a topic to work on, it could be interesting to pursue. Just as a notional concept, this is not formal, to give you a sense of what I mean. Here's a comparison of inductive inference and abductive inference in robotics. So we have a Bayes filter and what we could call an abductive filter, which is really the scientific method. So we start with some prior over some fact that we're trying to ascertain. Now facts are continuous. And we have an observation, and we update that with a posterior. So far it looks the same. But abduction requires us to form a hypothesis. And if we have only one observation, we say, well, that's probably the best belief we can form at the moment. But now we have a second observation, and we compute a second posterior. And now there's actually an update, right? And so Bayes rule normally is just going to blend them in some maximally likely way, whereas with abduction, we ask a question. Do we accept or reject the old hypothesis based on the new observation, right? And that is the key difference between induction and abduction. And that is the scientific method. So why abductive inference is important in robotics, it gives us a few really important things that induction does not. It gives us robustness to perturbations, and it promotes team confidence. So if we're navigating in a shared environment very close together, I want to believe with confidence that your possibly slightly wavering motion is indeed still trying to go between the two people and not to the right, right? So little noises shouldn't change my opinion about where I intend to go. And that brings us back to decision making, right? Because coarse-grained granularity corresponds to the team setting. And so this is actually an abductive result, that with abduction, you tend to get it's either this or it's that. It's not a continuum sort of result. All right. I'm going to bring it back down to earth now. I'm going to switch gears and talk in detail now about social robotics, pedestrian navigation. This has been a big effort in my team over the last several years. And it starts with a very simple story. We have a human and a robot in a hallway. They need to pass by each other without collision. And in order to do so, they need to do a few things, right? They need to observe, predict, plan, execute, deconflict. But really, in a team setting, this turns into receiving and broadcasting intent and coordinating repair. So we have repair again. All right. Now, they have two choices, right? They can either go to the left or they can go to the right. That's really all there is in this case. Later on, we're going to generalize beyond two people, though, and it gets more complex. Now, I want you to note, here we have a binomial distribution. So that is our representation, right? It's that distribution between left and right. One of the agents is going to take an action. So if you're in a hallway and you want to indicate that you want to pass on the right, you might move a little bit to the right side. Usually we do it subtly, but if you want to be forceful, you can actually take a big jump to the right. Usually that happens in big crowds or at the last minute. Either way, everybody observe this action that you take, and we update our distribution, and we say, does this change our hypothesis about your intention or not? So this action, that's our communication. And then updating the hypothesis, that's our coordination, right? And so the goal is for the two agents to agree on the distribution, and furthermore, to drive the distribution towards one end. Now, how do we generalize this beyond two robots, right? This distribution breaks down if you have a lot of agents, because really there's a lot of separate decisions that need to be made. So introducing the braid group from topology. This is a set of n strings, if we have n braids representing n robots. Two strings will cross. They can cross over or under corresponding to passing on the right or left. And we get to chain these individual generators together to produce more complicated group motions. So if we have n agents in a room, they're moving in space-time. Here's our trajectories. We can project these down onto the y time plane, preserve the ordering of the crossings, but tidy it up a little bit, and that gives us our braid. From this, we can extract what's called a braid word, which is a sequence of crossings or inverse crossings, so rights and lefts, that we are claiming is going to happen. Now, this can be a record of something that already transpired. It can also be a prediction about future events or some combination thereof. But what's crucial about this is that we took a continuum thing, the set of all agents' trajectories, and we've now compressed it into a countable entity, right? We've turned it from the geometric to the topological. And this is really important because now a robot can enumerate these things. It can assign probabilities to individual braids and reason about how likely it is that different braids are about to occur. So, all well and good. Braids are complicated. Maybe we want to stand back a little bit, though, because how do we assign these probabilities. Where do these braids come from? We need something that's grounded in the actual shape of people's paths. So turns out you can learn it, which we did show. You can also apply some common sense reasoning. So in this case, here we have a moment, a positive moment of the human and robot circling around each other. You can also get a negative moment, of course, if they move in the opposite direction. So the beginning of a moment, positive or negative, is an indicator of an intention to pass on one side or the other. That's a signal to the observers of what you want to happen. So that's part of a negotiation with the team about how we're all going to pass each other. Now, this turns out to capture a lot of the things that we need, angular momentum. First of all, clearance is encoded by the radius between the two agents. Legibility is encoded by the velocities of the two agents, both the direction and the magnitude. And thirdly, consensus is captured by the sum. So if these cancel out, then they disagree, right? If they contribute in the same direction, then they agree. So using this tool, using social momentum, we can actually manipulate momentum in order to convey intention to other agents in our proximity. We can formalize this still a little bit further by creating a dynamical system based on the winding numbers. So you can wind in a clockwise or counterclockwise direction by 1/2 and construct a vortex dynamics for collision avoidance, right? And what that looks like is a Hamiltonian where we have a generalized coordinate, which is the distance that the agents are from each other, and then the conjugate momentum. And the idea is that we want to conserve momentum. And so this Hamiltonian is constructed so that the geodesic, or the straight line, if you will, is actually moving in an orbit. So maintaining this winding number direction around one another. And therefore, the conjugate momentum is actually constant as you orbit. And this allows us to follow a direction in maximum increase or decrease of the winding number. Now, we don't want agents to just spin around each other forever. What we actually want is a controller that uses this to help agents get where they're going while preserving a topology. So we're going to start with a topological specification. This is a complete or incomplete specification of pairs. So how do agents 1 and 2 avoid each other? How do 1 and 3 avoid each other, et cetera? You don't need to specify all of them. So unlike the braid group that I showed earlier, this can be incomplete. And from that, we're going to construct a potential field, which is going to use the goal as an attractive potential, and the Hamiltonian is going to give you repulsive potentials and flow. And that gives you a nice, smooth motion. And you might ask, well, people don't orbit around each other when they pass. And that it turns out in practice that you don't get these circular orbits because it is a potential field. They actually flow nicely around each other. But unlike other optimization methods, this is orders of magnitude faster to execute. And it also gives you a topological guarantee. Whereas if you just tried to, say, optimize the shape of the curve, it's very tempting to flip the topological class if that makes the path shorter or smoother or whatever it is that you're trying to do. All right, so what does this look like in practice? It's all nice theory, but let's try a user study where we put this on a real robot. In this setting, we put hard hats on the users, actually to track them with Bicon, but we told them it was a factory setting, so that's the story. It was a simple analog where they had to drill holes. Drilling a hole means writing a square on the easel. And then they had to fill in the holes with fasteners by putting a sticky note over top of the hole. And they had to do that while moving from station to station. And the robot was there to supervise them, right? That was the robot's the manager. So the robot was going to move around and observe their work. And they had to, every time they moved, they could not move to an adjacent easel. They had to cross the room. Why did we go to all this trouble? Because if you tell people, I'm going to watch the way you walk, don't mind me, just walk normally, it doesn't work, right? So we had to distract them and act like we were studying this manufacturing question instead. Meanwhile, we were actually just looking at the way that they walk in the presence of the robot. And it was designed to construct these kind of close quarters motions where you tend to get really interesting behavior and where it can get really awkward if if you're about to run into somebody, right? Okay, so we had a few conditions that we tested. One that we compared against is ORCA, which is reciprocal collision avoidance. This is very frequently used in animation. It assumes that all of the agents are running it. That's the reciprocal part. And we, of course, didn't know that our humans would comply, but it turned out to work fine in practice. The second condition was teleoperation. Because we were using a beam, it's already a telepresence platform. We could put a trained operator on the other end and just act like a robot. Third one was our social momentum that I just described. And I'll play the animations again. They didn't quite play earlier. You notice the ORCA, they all kind of rush toward the middle because it's trying to do the minimum deviation in velocity space. Whereas social momentum, they're trying to be much more legible, so they take a bigger deviation from that shortest path. There are a variety of metrics that we looked at in this space. Geometric efficiency, acceleration, energy efficiency, topological complexity. I should note, the first three are functions of a single trajectory, whereas this is actually a function of all the trajectories. It's measuring how entangled they are. Less entangled trajectories are easier to follow, easier to comprehend. And then we use some qualitative metrics as well. So, sound effects for the factory. And that's what it looked like in practice. It's actually pretty smooth motion. It's pretty intuitive. It does move slower than people, which we did for safety. But just the gut check, it feels passably good. Yep. How do the people react to the robot? So this is why we have metrics, so you don't have to just stare at the robot. So, yeah, question?
Yeah, so what is the goal here? I mean, you talk about the team,
Yeah.
but here just collision avoidance, right?
Right, it's just, that is it.
I mean, swarms have solved the team.
Okay, but
They're a team, they have consensus.
if you have a swarm,
They have a barrier certificate.
yep, yep, no question.
That you showed with the turning around is basically to avoid
Right,
the deadlocks.
yep.
And of course,
Yep, so totally true. So you can take a set of swarms, all artificial agents, and they can all avoid each other. They're using an artificial protocol to do it. It's different than what people do, right? If you put one of these agents among people, you can still have it be safe, but it's not going to be intuitive motion. It's going to be motion that people don't understand. That's really the key here. This.
but here it's not a matter of people understanding. People are acting, and since they see each other, they are reacting and avoiding each other, like
Yeah.
we do every day.
Yeah,
And so it does
Right.
not matter whether I understand it, I just do it.
right. Okay, so basically, I watched this video 3 times. I don't see anything, right? That's kind of the question, I think. And that's exactly the point, right? Some research, when you don't notice anything out of the ordinary, that actually means it worked well. I had the
This is people. People are good.
yeah, people are good.
So that's what I'm trying to
Yeah.
say. This is
No, I mean, we showed the algorithm in theory in simulation with other agents, and that works great too. But then the question is, does it also work with real people? They're both equally important questions, right? We want to send a robot out into the world. It needs to work with people.
So the question, of course, is what do you compare it against?
Yes. So I showed you the baselines we used.
With people.
Yeah,
Is that what you
they-
use with people?
Yeah, those 3 baselines with people. Yeah.
I mean, what I would love to see is the same scene without the robot.
Without the robot, just people. I don't have that video for you.
Still are collision avoidance.
Yeah,
But,
yeah.
not without the robot.
That's so one of the things about HRI, which the HRI researchers in the room can testify to, anytime you show a result, people are going to say, well, what about this condition? What about that condition? There's a zillion conditions I would have loved to test. Unfortunately, we didn't get to test all of them. I think these are great questions. Yeah.
So first, the people are just wandering on their own, that they're not following your algorithm, right?
That's right. That's the point.
So the second thing is, Srinivas's point
Mhm.
is, if the robot weren't there,
Right.
people would
They would still be doing the same thing.
do the same thing.
Yeah.
And then if the robot's there, they do the same thing. which
Right.
we don't understand what
Okay. So what the interaction is subtle because when I pass you in the hallway, that's also a subtle interaction. We don't think of that as teamwork. Technically it is because we have to come to consensus. We're flipping a virtual coin to decide if we're going to pass on the left or the right. It happens very transparently because humans are so good at it. So you don't think about it as teamwork, but technically it is.
So we are talking about results here and so on.
Yeah.
So what is your hypothesis? Because if I'm a human-robot interaction,
Yep.
or a human-computer interaction, or a human factors person,
Yes.
then I say I do this experiment that is a controlled experiment.
Yes.
And I have falsifiable hypothesis.
Please read the paper. It's all in there in great detail. I mean, the point of this talk is to give you a sampling of a lot of work that I've done. Of course, there's a lot more details in the paper. Yeah.
Let me just so just because we have the
I know we need to
reception at 4:30,
wrap up.
we want to rush Ross.
I'm near the end, actually.
If you have a question, why don't you flip a coin in your head? If it's heads, it lands, then ask the question. If it's tails, ask the reception.
All right. Very good. So I'm just going to give you a little sense of the results. I'm not going to go through all of the results here. We had 105 participants, so it was a pretty big study. And so the first question we asked was around how did the robot behave? And we wanted to see if the robot was behaving differently, if we could perceive differences in close proximity to humans. Now, there were hypotheses. It was all scientifically valid. Here I'm just giving a few of the takeaways. Firstly, that Orca generates the most geometrically efficient paths. This is not surprising because that's how it's designed to be. Social momentum generates the highest acceleration paths because it's trying to be the most legible. In some sense, it's actually trying to burn energy to be clearer to you what it's trying to do. Telepresence, on the other hand, generated the most energy efficient paths and also the least topologically complex paths. So that says there's something about the topology we still have not captured that the human remote operator seemed to be doing a little bit better than our algorithm. So what that says to me is that there is still room for more study in here. Even though, subjectively, watching the video, it looks like everything is fine, there's still subtleties to social navigation that we don't really understand yet. The second thing that we wanted to measure was human behavior. We wanted to see how are people reacting to the robot. In close proximity, we noted that people have the lowest acceleration paths around our social momentum. And that was actually a really good result because it says that people are not having to be surprised by what the robot is going to do. They're prepared ahead of time and they don't need to react at the last minute. So that's actually good news. That says that there is an effect here. Something interesting is going on. We also looked at qualitative metrics. We wanted to know human impressions. Did they like one or the other better? These were all negative results. So people didn't notice any difference. So you could say, hey, none of this matters because people don't care. I will argue that navigation is something that happens at a low enough level. You're busy focusing on your task. You're not thinking about the efficiency of our effort at walking. So I think that there are effects that are real and important in efficiency. And my research, my earlier experience, such as the video I played at the beginning, shows that robots can cause really bad behavior among people if they're not being socially competent, right? So that's actually what we're trying to avoid in this case. All right, so I'd like to close here. These are the main points that I mentioned earlier, and I know that we are over time. So thank you very much for staying long, and I am happy to take questions. Oh, in the back, yeah.
So one thing about sort of social navigation is that people have very strong prior about which direction they're going.
Yes.
left or right sort of culturally. And my understanding is that the sort of social momentum framework doesn't use that. And you sort of mentioned the utility of priors in some of the
Yeah.
communication work. Is that the sort of thing that
It can use that, actually. So the winding numbers can be biased towards going in a positive direction, for example. If you're interested in social navigation, try walking around in Narita Airport for a while, because you've got people from all over the world and they have no idea which side to pass on. So you don't realize how hard navigation is until you've tried that. But yeah, actually we do incorporate, when the virtual coin flip I mentioned, that's a biased coin based on what country you're in. All right, so I will see you all at the reception. Thank you.